Welcome back, everyone, to the Chili Dan and Kirsch Mackey Design Review series. And in our previous video, you should have seen how Dan dismantled that schematic and broke it down so we could clearly understand all the great design choices that the designer made. So you want to check that out. And also where some things could be tweaked and some speculation on what can be changed and modified as well. So you want to check out that video. Next, we are in this PCB design phase where we are going to analyze the PCB stack up and the nuances and details in here. Okay, the schematic directly affects, of course, the PCB layout. And I'm going to go ahead and pass it to Dan so we could review this PCB stack up. Dan?
Good day, everyone. It's a pleasure to be back again. I do hope that you were able to look at the schematic review and understand some of the discussion there. We're trying to connect the behaviors of electromagnetic fields to the art and science of PCB design. We talked about the schematic because that's the foundation of the board. And what I want to do now is to look at every layer. This is a 4-layer board. And this is probably the most popular board stack that's out there in products. It provides a very solid platform that can be used to achieve multiple levels of compliance. It's quite popular in automotive, which has a very high level of importance for EMC and reliability. And we want to start, this is layer 1. What I like here is that they have used all the unused space is ground flood. And in my world, I want to continue to push the idea. If I paid for it, I'm not giving it back. So I have a minimum etch perspective. I only want to take the copper away where it doesn't need to be doing something. So in this case, I've got a lot of nice surface area. What happens here is it improves the fidelity of your fabrication process because it takes less acid to remove less copper. So you have your acid etch process is going to be more accurate. From a perspective of ESD, having lots of open flat surface provides a very attractive place for an impulse of energy to find and dissipate itself because you're achieving a lower impedance by having a large surface for this energy to distribute across of it. So these are things that fall out from that very beginning. So we want to think about reducing the amount of copper you take off and how you can effectively use this ground flood to improve the overall behavior of your system, both functionally and from a EMC robustness perspective. I've seen some videos where people are talking about this being an idea that's not as effective as I try to push it for, but it's true if it's not properly implemented. And we'll talk about some of the issues with the way this board was done and how they can improve the behavior of this ground flood. Because right now there's places we could make a difference. So layer 1 is components and routing, which is a typical outer layer. Let's look at layer 2.
Got you.
Ideally, layer 2 would be a solid ground plane. So let's cross our fingers and see what we've got on layer 2. And I like this a lot. This is an unbroken ground plane. This gives layer 1, anything on layer 1 automatically now has a well-defined transmission line for the energies that we're trying to deal with. So the energy between components and traces on layer 1 is in the space between layer 1 and layer 2. It's in that dielectric. All the energy that the switches, the transistors, the ICs, all of those components are managing energy that's in the space between layer 1 and layer 2. That's your well-defined transmission line for that energy. So let's look at layer 3.
Well, to piggyback off that and to make sure I understand, Dan, yes. I'm going to pull up the cross-section of this PCB stack up. You just said the transmission line and the space. When we're talking about the layers,
dielectric. between layer 1 and layer 2 is where the energy lives.
So like right in between here with
In
the
there, in the FR4, that's where the energy is. The ICs are just switches, and the resistors and capacitors are things that do something to the field in the space between their placement on the outer layer and the next ground plane. All that energy flows in the dielectric, and these components modify the way that flows. A resistor will convert a certain amount of the field that's moving in the space adjacent to it into heat. A capacitor will catch a certain amount of that energy and store it. The same thing with an inductor. An inductor will store energy in the space between the body of the inductor and the ground plane on layer 2. An IC will take energy from an input pin that comes in from the space between layer 1 and layer 2 through the body of the IC and layer 2 and to the output pin, and it's delivered to the space between the trace on layer 1 and layer 2. So all that energy is traveling in the dielectric. That's the FR4 between the layer 1 copper and the components and the layer 2 copper. That's an intact transmission line. If it needs to be special, meaning it might need to be a controlled impedance, there are tools to allow you to adjust both the thickness of the dielectric and the width of the trace in order to achieve the required impedance. But the foundation is to make sure that there's only one space between each conductor and ground. And that's what you get with layer 1 on top of layer 2.
Oh, so that's why you're so happy that layer 1 that we just looked at has your components and some signals, traces, but that the layer 2 was solid ground, because you're saying the connection between the signal traces and ground makes the transmission line.
That's the transmission line. And I don't have to worry about breaks there where I have to avoid crossing over breaks in the transmission line, because both conductors need to be intact. The ground plane, which is the continuous conductor from power supply to IC to load, cannot be broken. Next to that is the continuous dielectric, which is where the energy flows. The signal trace and the ICs are what I call the switched conductors. So those are the third element to manage the field energy. And the switched conductor goes through the body of an IC, and it turns on and off and either allows or disallows the movement of field by whether the switch is opened or closed. And so that distribution of energy from source to destination is intact in that space. Now, we can't do everything we need to do in this case in a single layer of components and routing, or we would do this in a 2-layer board. The 4-layer board, we now have layer 3, which is on the other side of layer 2. Layer 3 is just as happy as layer 1 because all of its conductors are next to the ground on layer 2. So we have another space where the signals that are on 3 are happy because they're next to 2. Signals R1 are happy because they're next to 3. And the bonus is when you route from 1 to 3, that the dielectrics are connected automatically by the hole around the signal via. So you go from the space between 1 and 2 to the space between the edge of the foil on 2 and the via into the space between the bottom of the ground plane on 2 and the top of the copper on layer 3. So the transmission line is intact because both the continuous conductor or ground is never broken and the signal is never broken. So that path is intact in 3 dimensions. So energy from 1 to 3 is automatically a good transmission line. So this makes this a very solid start for the board. So let's go to layer 3 and take a look at it, and we'll see what's happening on 3. So in this layer, they have, I'm assuming these shapes are power distribution shapes, and we will get into some discussions about what can and can't be done to improve this. Quite often, the shapes of the power supplies are designed to just fill the space up. But when I do it, I make sure that the shapes are defined by where things are connected to it. And we'll get into that when we discuss the power supply routing, because if you do that, then you can change the shapes so that they're smaller. You don't need to have power routed all over the place. A really good example, I think, would be if you can go to the left down a little bit. So there's a horizontal conductor there, right there under your cursor. On the left-hand side, there's 5 vias together there, but there's all this copper above the top of it. There's nothing happening up there because there's no via there. We made this trace really wide because we think we're supposed to, but it really has not really made things better. And then we'll talk more about this. Blobs of via of the same signal, whether it be ground or power, by themselves to the fields appear to be a single conductor. So the energy in the z-axis is between signal or power via, or signal or power via grouping, and the nearest ground. So I've got a blob of power here and ground's over here. The energy's in that space. So the resulting impedance is not because I have all these power vias together. It's because it's what's the space between the power and the ground. So we'll look at, in the power supply design part of this, we're going to talk about why this is a bad idea and how we can improve it without even having to add more vias. So
wow.
This is critical. You have to think in 3 dimensions. What dielectric did the signal start in? What dielectric do I want it to end up at? And what things do I need to do to provide the amount of energy or the type of energy that's required for the job to be done? If it's a high frequency signal, I need to be conscious of the impedance of all 3 dimensions of the transmission line. If it's energy, I have the same issue. I need to make sure that the impedance is low enough that it will allow me to deliver the energy properly from where it's coming from to where I'm going to use that energy. So these are things I look for, blobs of vias that are by themselves. And that's based on the old philosophy of resistance-based design. I got 10 vias, 10 conductors in parallel. The resulting resistance is 1/10. The resulting impedance is not. The resulting impedance has not changed just because I used a bigger via or I used a whole bunch of them together. The z-axis impedance is a function of the space between the 2 conductors that you're using to deliver the energy.
Wow. So in doing this 2D routing and dropping vias in here, I can't just be thinking in the 2D, how much resistance, a lower, it doesn't automatically mean I have lower impedance just because I have more vias. I have to really think about the 3D geometry, what space, what dielectric is being used up, where the energy is being routed in the dielectric.
Correct.
Wow.
You know, how big is the bucket? I haven't made the bucket bigger by making the walls thicker. One of my analogies is if I have a 1-inch hose and it's good for 5 gallons a minute, and I need 10 gallons a minute, and I make the hose out of steel instead of rubber, it's still the same diameter hose. I haven't changed the capacity of the hose. If I need 10 gallons a minute, I need a 5-gallon-a-minute hose, or I need 2 5-gallon-a-minute hoses in parallel. So to improve this, and this is a sneak preview, I would replace every other power via with a ground via. To make it even better, I would make them in a matrix. And each discrete power and ground via is now a separate dielectric, hoses in parallel. And if you look at today's high performance ICs, the core supplies specifically are a checkerboard where they've got interleaved power and ground vias. It's to increase the number of transmission lines that you can connect the die to your circuit board with. It's all about the spaces and the impedance that we're going to have. I could probably reduce the number of vias and achieve better energy delivery. So this is the thoughts. We're trying to build some aha moments for you in the future when we get deeper into this, specifically addressing power supplies. But this was one of the things I look for. What are these shapes? Why are they shaped the way they are? And are they doing any real work? If these power shapes are not doing any real work, whether it be the vias or the fact that this trace is 40 mils wide or however big it is, I want to rethink that approach, make the shapes so that I achieve the impedance that I want. So let's scroll a little bit out, zoom out a little bit more. I want to point something out. So on the upper right-hand side, there's a narrow piece of this transmission line. You see where it gets narrowed down?
Right around here.
The maximum energy that can go from left to right or right to left is managed by that impedance. So anything wider isn't going to make it better, even if there were a bunch of vias here and a bunch of vias there. Because that's a pinch point. It's where the flow is restricted. If I go from a 4-inch hose to a 1-inch hose to a 4-inch hose, what limits the flow of water? The 1-inch hose.
The 1-inch hose.
This is my 1-inch hose, and these are the 5-inch hoses. It didn't make it any better by going to 5-inch hoses. So I can use that copper for something else. Routing signals, I can do all kinds of stuff. If I don't have a better use for it, then ground flood, which is better. If I'm not going to do anything useful, ground flood is always useful. And we'll talk about how to make sure it's done correctly. So these are the things I would look at in the power layer. Minimize the shapes so that they're doing real work, and then improve my routing density for other things that I can route on the signal on this layer, and or put ground on there, which in this case, because I've got another layer to worry about, I can help improve the outcome for routing that's going to be done on what I call the orphan layer. So we now go from layer 1, 2, and 3, which are a paired dielectric stack. The dielectric between 1 and 2 is automatically paired with the dielectric between 2 and 3 because there's holes. If you route from 1 to 3, there's a hole around the via. That's the space. You continuous dielectric, continuous ground conductor, and continuous signal conductor all form an unbroken path. So let's zoom back out and look at layer 4.
Okay. This is layer 4.
Okay, in this board, they do not have components on the secondary side, which is interesting because this is a 4-layer board, right?
Yeah, it's a 4-layer board.
Okay. So they're not putting components that doesn't look like on this. We've got routing and we've got ground flood, which is great. The problem is most people think that layer 4 can return on layer 2. That's not the case. You have to have unbroken, nothing between the signals and ground. So in the z-axis, there's 2 dielectrics and a signal layer between layer 4 and layer 2. Layer 4 has to be considered as if it was a single layer board. So all the routing at a minimum needs to be done with continuous coplanar ground copper. So next to every signal from the via that brings it there to the via that takes it away needs to have continuous ground copper next to it at a minimum. So when we look at the top corner of this board, there's a trace that goes from where your cursor is to the right. Well, that one's not so much. The one to the right that's at the top, that one there. So when you see how that's routed, it goes from left to right, but it doesn't have continuous ground copper next to it. It's bad is that if the only ground copper, it has to go find, when it gets to this point where your cursor's at, that peninsula, when it gets out there by itself, it doesn't know where the other ground is, but it has to find it. So that field spreads out all over the place, looking to keep that continuous conductor next to it. It doesn't have any choice. It has to. So those are the things you look at when you're on a single layer board, which layer 4 of a 4-layer stack with ground plane on 2 is a single layer board. So the first challenge is to make sure you always have continuous coplanar ground copper for each signal, and they can share it. If they had moved that trace underneath your cursor, underneath the one that's highlighted, and so that the ground flood could fill between them, then they could achieve that with the coplanar ground copper.
So if I'm imagining,
I don't have copper on 2 to work with, it's not close enough.
If I'm imagining this correctly, so the field is, say, traveling on here and the -5 VA, and it's happy with ground being around here, but
it's a start. But yeah, because it's got ground next to it. Once it gets to the end of peninsula, there's other things wrong here that I don't want to talk about now. It has to somehow find its way back to that ground that's it left behind.
Oh, when you say left behind, I'm going to pull up the
So
stack.
once it goes,
it left behind in
it's in the space between the ground flood and the signal. And then when the ground plane's gone, it has to find, where did this go? So the signal is trying to go out here, but the field is expanding and finding its way, even if it has to go back underneath the ground on the top. It goes to the top of the ground flood on 4, find a ground via and find its way around to get somewhere over here. So you get this huge discontinuity in the flow of energy. It takes longer, and these wave fronts are out there kicking everything that it touches. So you've got multiple wave fronts, and everywhere the E field touches another conductor, it can't go through it. It's going to cause a magnetic field to be created, and that's going to increase crosstalk, increase losses, and just make things bad.
So because we don't have a continuous ground here, a ground next to this field is traversing the,
it has
the
to
3D,
find way, yeah.
Going through the dielectric above it.
It has to go. It doesn't know where it's at. So the field is going up out of the board. It's going down into the board horizontally, and it's going down into the board or up into the board vertically, because we're on layer 4, until it finds the other end. It has to find it. The railroad tracks have to be continuous. If we don't make it that path that we choose, the fields have no choice. That energy has to find its way to the continuous conductor. And if we don't make it something of our choice, the results are not good. So this is why an orphan layer board is very important to do it. So this is my evaluation of this board stack. Another comment is you've got these 3 connector pins, no, to the right where you've got the connector pins. One of the rules that I give my teams is you use the smallest drill size that your fabricator will allow based on the thickness of your board. Because unless you're putting something in that hole, it's better to let it fill with copper during the plating process. It's better thermally, better mechanically, lots of good things. So in this case, I've got connector pins going into these holes. Therefore, the size of the holes is determined by what is appropriate for putting something in the hole. The vias that I'm seeing around here should all be the smallest drill that can be used. It improves routing density, and again, improves that mechanical fill during the plating process, which improves the thermal performance. Because you've got a solid piece of copper, that's pretty much a solid piece of copper that's allowing the kinetic energy or heat to move through the board stack. So I don't ever pay for conductive fill. I use lots of small vias filled with copper because it's better and it's free. Effective It means using the materials that you're paying for to their very best capability. And this is a great shot. You've got these -5-volt vias, and there's a big shape of copper there, what one of them is connected to. But the nearest ground is pretty far away.
Yeah, nowhere in sight almost.
There's one up on the other shape. So this is what we want to talk about when we get into the how to make layer 4 better. So this is the evaluation for the board stack. Again, if a layer on your circuit board is not adjacent to a ground plane, don't believe that it's going to find its way safely to another space. A 4-layer board with layer 2 ground, 1 and 3 provide you a very solid platform. They're paired dielectrics. When you move energy from 1 to 3, it's automatically a connected dielectric. I call those it's a triplet or a paired dielectric. Layer 4 is not next to 2. You can't think of it that way. It's by itself. It has to be routed with coplanar grounds. And then when you route from 1 or 3 to layer 4, it requires a ground transition via to connect the dielectric between 1 and 2 or 2 and 3 into the horizontal dielectric between the copper flood of ground and the signal on 4. It's by itself. You have to route there with both conductors. So that's a setup for when we come back to discuss how do we do an orphan layer, and we're going to do another segment also on how to improve power supply design. So I hope this has been some good food for thought. My favorite board stack, if you've listened to me before, is a 6-layer board. Layer 2 and layer 5 are ground. I've got 1 and 3 automatically paired dielectrics. I got 4 and 6 automatically paired dielectrics. And I only have to worry about when I route from 1 or 3 to 4 or 6 with ground transition vias. And so I do as much of the lifting as I can with components on the outer layers in their adjacent paired dielectric space. And then if I do need to transition into the second triplet or the second dielectric pair, I will then make sure I have a ground transition via that allows me to connect with a well-defined Z-axis transmission line. So my board stacks are typically going to be even multiples of 3. So 6, 12, 18. If I do an 8-layer board, it's going to have 3 ground planes in it.
Wow.
If I do a 4-layer board, I don't have that luxury. I have a good philosophy for how to do layer 4 correctly. And I've helped my automotive customers with hundreds of designs where they've successfully been able to implement a 4-layer design with automotive. In fact, I have a 2-layer board that one of my customers did. We were able to achieve automotive compliance with a 2-layer board with quad flat pack micros and judiciously, properly using the idea of triplets in the coplanar space and making sure we took good care of routing between these, because a 2-layer board is 2 single-layer boards.
A 2-layer board is 2 single-layer
boards, unless you have the luxury of making one of them solid ground. So that's the philosophy we have to try to think about. So this is what I hope you guys will all think about and watch for our next video, where we start to talk about how do we make these things work in order to be able to have a product that is both robust and cost effective. So thank you again. And remember, it's all about the space.